In this episode of The Bear Roars, Dan chats with Matthew Kinsella, CEO of Infleqtion, the world's leading quantum information company. Infleqtion is a trusted supplier of high-precision components for research labs in quantum machine development. Prior to his role as CEO, Matthew served as a partner at Maverick Ventures, leading investments across the technology industry, including Maverick's investment in Infleqtion. Join us as we dive into all things quantum, including atom modality, Albert Einstein's spooky action at a distance, superposition, timekeeping, and more. Let's poke the bear to kick off the conversation.
Well, Matt, thank you for being on here. This is going to be a fun one. One of my favorite topics, quantum.
Thanks, Dan. It's really good to be here. Thanks for having me.
Absolutely. So tell us your first memory of quantum. When did you first come across quantum and what quantum was, and how did you process that? What did it mean to you when you first started to get exposed to it?
So I first started going down the quantum rabbit hole, for lack of a better term.
That is a good term.
It's a deep and winding rabbit hole for sure. Back in 2017. So the firm I was working at the time, Maverick Ventures, where I was for almost 19 years, was structured as an evergreen fund, which meant we could take very long-term views on our investments. And because of that, we would do these quarterly, what's the world going to look like in 10 years type meetings. And I think I had read about quantum in an Economist article, honestly, in 2017. And I thought, okay, well, this is probably something that's going to be important over the next 10 years. And so I started reading about it and dabbling in it and started to meet some companies that were around back then and got very, very intrigued. It's one of these rabbit holes that once you go down it, it's like kind of nothing else seems interesting at that point in time. So I met a number of different companies. And the conclusion I walked away with at that time was it was a little early to bet on any existing company. And so I started thinking, well, maybe it would be interesting to start a company from scratch. And so I then started going down a different rabbit hole.
Before we go there, when you first started to learn about quantum itself, what was going through your mind from not a business sense, like how might I go down the investment path? We'll come to that next, but from what is this thing called quantum?
Absolutely. Well, it was mind-boggling. I mean, it's, you live your life at this macro level that abides by rules that make sense to you because you can observe them, largely sort of defined as the Newtonian laws of physics. But then you learn down at this quantum level, the world of the very small, it plays by a whole different set of rules that don't make any sense at all. You just have to accept that they exist. And it's very humbling in many ways because
it's a good way to put it.
It doesn't make sense, but it's absolutely incredible. And it's the fundamental way the universe works.
Yeah. And one thing that was really interesting to me when I first started to trip across it many years ago was the history behind how it was discovered. The steps along the way, the revelations, the nonsensical aspects of it that were fought so hard against because at our human existence, it makes no sense. And so the smartest people in the world, including one by the name of Einstein, said that cannot possibly be right. And it took decades of experiments, starting first with maybe thought experiments, math that suggested things existed differently than our awareness, and then leading to the actual experimentation to try to prove or disprove that this could possibly be real. So that history is probably what fascinated me the most. That and that it was discovered first in math. Like math unveiled the secrets of the real world, which was kind of like, maybe sometimes you just really have to put more trust in math than I would have ever thought. How can math reveal something to be true on a physical sense that otherwise we had no sense of?
Absolutely. And there's I've thought more about this recently, but thought about it when I first learned about quantum too, which we don't need to go down. This is a total separate rabbit hole, but there's a very interesting philosophical and religious aspect to this too, in that if you look to history, religion has sort of occupied that space that can't be explained by what you see. And that space was wide 1,000 years ago and has gotten narrow and narrow and narrower. And it makes me wonder, quantum we can't explain. And so what is what is actually behind all of it? And so not saying it's a religious thing, but it's kind of similar in that it is that little sliver of the world that we still don't yet know how to explain. We can explain it with math, but it doesn't make sense as to why the world works that way.
Yeah, what's interesting about that is, on one hand, the purview of religion has often been what is beyond us as humankind's ability to understand. That's where kind of religion has naturally taken over, which has changed dramatically over the eons.
Absolutely.
But there's something maybe a little bit different about quantum in that quantum, within the realm of quantum, as you understand it deeper, there's physical processes that can happen that blend what might be happening in a physical place with another physical place, a connection that you can let your mind wander. What does that really mean? Is there a deeper meaning than just, hey, accept the fact that that's how the world works? And well, I'm sure we'll get to it, but the concept of entanglement and teleportation, which is the manifestation of how you move, not just information. We know how to move information from one place to another.
You know
in the quantum world.
Well.
I know how to do that very well. But this is different in that you would actually, I want to be careful because this isn't moving matter from one place to another, but it literally is eliminating something that we would think of as an object,
right?
Eliminating its existence from one place, and it not quite immediately because you got to have the speed of light, but at the speed of light, it reappearing at another place,
right?
So literally teleporting from here to there. Well, what does that really mean? We are not on the cusp of understanding the broader implications of that.
No.
But we know it to be true because, people who work for you do that.
That's right. And they can observe it. Yes.
Yeah, and they can observe it. Okay, so now let's get back to, now you're discovering this thing.
Yes.
My mind is blown. As an investor.
Yes.
You're like, hey, this might be a good area of investment focus if you have a long-term horizon. 2017. Okay, now we're 2024 and you're thinking, hey, I could think over a decade. So take us more through that thinking on the investment side that you started to go down.
Sure. So given how early we were then in humanity's journey towards commercializing quantum, I thought, and how early we still are today, honestly, but back then, even earlier, I thought maybe an interesting route to take here. My old firm, Maverick Ventures, focused on very early stage investments. So maybe an interesting route to take would be to actually partner with a professor and start a company from scratch. So I started meeting various professors who were doing amazing research in their various fields, all focused on a different modality on how you could isolate the quantum particles that you're going to utilize to do interesting things with. And ultimately found my way to a gentleman named Dana Anderson, who you know and had met even before I had. And Dana was a pioneer in a modality that hadn't been as explored as some of the other modalities back then, called neutral atoms. And as I learned about neutral atoms from Dana, I became quite enamored with them, largely because they were highly flexible. You could do a lot of different interesting things with them. And so my mind started to go to, well, what kind of products could we build here? What kind of business could we build? And Dana had actually been operating a company, which was then called Cold Quanta, which was effectively a bit of an extension of his lab at CU Boulder, but they were making...
Let's take a pause here and let's talk about what you mean by modalities and what you mean by the cold atom modality. And let me set that up a little bit. And when we think about the world of quantum, you mentioned the world of the very small, but it's also the world of the very cold.
Yes.
And motionless.
Correct.
So talk a little bit about what you mean by modality in general, and then what is different about the cold atom modality than some of the other modalities.
Sure. You're exactly right. So it's the very small and the very cold. And the reason you need things to be very cold for quantum is you really need to, in order for these atoms or other particles to exhibit some of these very bizarre things that Dan and I keep teasing at, but we'll dive into what those are. But in order for those to start to manifest themselves, you effectively need to remove all external forces from them. These are very fragile states. And that's one of the reasons why we don't experience some of these things up at the macro level, because all the noise that surrounds us on a daily basis makes those collapse into collapse out of the really strange state they could be in. And so how can you remove all of that external noise? Well, you can freeze these atoms, and you can freeze them in a couple of different ways. One of those ways would be naturally put them into a dilution fridge, which is one of the quantum modalities.
So put them in a very, very cold environment.
Very, very cold environment. Yes.
Yeah, so colder than outer space.
Colder than outer space. Yes, exactly. So you stepped into that fridge, you would turn into an icicle right away. And so you wouldn't want to go there. But another way, if you think about what is frozen is actually the lack of motion of atoms. And so some of the foundational work that Dana had been a pioneer of at CU Boulder, and several Nobel Prizes were won along the years, going back to the mid to late 90s to more recently, was what's called atom cooling. And that's holding atoms in place by hitting them with a series of lasers from multiple sides, such that that atom is not moving at all anymore, or very, very, very barely moving. And it's residing inside an ultra-high vacuum glass cell. And so again, if you think about what is frozen, it's the lack of motion of atoms. These atoms are actually the coldest place in the known universe, even though the glass cell they exist in is at room temperature. So it's a bit of a mind-boggling thing to conceptualize, but these are the coldest places in the known universe. So they are cold, but they're existing at room temperature within the system that they live in.
Yeah, so just the way physics works, why it works this way, we don't know, but the way physics works is if you tune to a very, very, very precise color of light.
Correct.
That is dialed into the type of atom you're pointing it to.
Correct.
So any type of atom has a very precise light that if it connects to that light, it just loses all motion.
Right.
Might be an unscientific way to explain it, but if
exactly
you know
right.
what that
Yep.
frequency is, that
That's
color
right.
light, and you have a way of pointing at the atom, it becomes motionless, which is the same thing as being
Frozen.
very, very, very cold.
That's right. Yes.
And that's what the work that was done out of CU Boulder and NIST and Dana was involved with is, how to, take that notion of science and turn it into something that you can engineer and make useful into devices. And we'll talk about what kind of devices. So let's see where we're at in that. So that, and other modalities, maybe just rattle off, we won't explain the other modalities, but as examples of other modalities that aren't cold quanta, cold atoms are
Sure.
what range?
Sure. And when we say modality, just to put a fine point on it, we mean how are you making the material at the very small level cold such that you can do interesting things with its quantum state. And so there's superconducting, which is taking actual physical qubits, which is a quantum bit made of some superconducting material, then put into a dilution fridge. And then those bits will start to exhibit quantum properties, and then you can entangle them and start to build circuits with them. There's trapped ions, which is not terribly dissimilar from neutral atoms, except you're using charged particles, which you were talking about, colors of light. Those react to microwave wavelengths, so they're a bit easier to control. And so trapped ions as a modality have been around for a bit longer than neutral atoms. Some of the issues you run into with trapped ions, though, is because of that charge, those ions interfere with each other, but we don't need to get too deep into that. But those are two other modalities. There's all sorts of other ones. There's electrons over helium. There's photonic type modalities. There's actually using diamonds to create quantum computers. So there's many different modalities, but the one we focus on is neutral atoms.
For the first time, Dan Caruso pulls back the curtain in his book Bandwidth, a memoir that celebrates the pioneers who invented the internet's early backbones, the renegades who lit the fiber revolution, the antics that caused the biggest market crash of all time, and the new wave of entrepreneurs who led the industry back from its ashes. Though it seemed to happen in the blink of an eye, the Bandwidth adventure was a multi-decade roller coaster ride involving larger-than-life successes and devastating failures. The unbridled ambition of newly minted billionaires and high-profile tycoons created extraordinary value, unprecedented value destruction, and endless opportunities for a brave few. This reflects tech's past, present, and future, and is a story you won't soon forget. It will help you prosper during today's AI tech bubble. The book is available for pre-order at dan-caruso.com/bandwidthbook and released in early 2025.
Yep, and we're going to talk more about that. Let's go into that one tangent that you mentioned, but we didn't go into. When we talk about the strangeness of the quantum world, how could you help our listeners understand what happens in strange ways in this quantum realm once you're in it?
Sure. So down at this world of the very small, we've already established things just behave differently. Things are measured, things happen in probabilities. And so nothing is necessarily certain at that level. And so that means some very interesting phenomena manifest themselves. One is this concept of what's called superposition. And so down at this level of the very small, an atom can exist in many states at once. And to make it even more mind-boggling is once you observe that atom, it will collapse into one of those states. This is one of these things that doesn't make any sense. The act of observation actually influences the actual state of the atom. It's one of those things you just have to accept is what it is. And so that's a concept called superposition. It can be very useful for creating computers over time, which we'll get into. But that's one of those strange phenomena. I'm sure you have a way of explaining superposition. How do you usually explain it?
That at the qubit level, qubit meaning whatever that material you're using that goes in a quantum state, it can exist in lots of states at the same time. It's not in the world we're all familiar with, the digital world. You have ones and zeros. So all digital devices, before you get into quantum, are really just a series of taking ones and zeros and using that to encode information.
Right.
And so if you want a faster a faster classic computer, you just have to run through those ones and zeros more quickly than the older technology. But when you get to the qubit world, one of these factors of superposition is, and now that same, singular particle, instead of being a 1 or 0, it's a combination of ones and zeros all at the same time.
Right.
So you then get how do you harness that? So that's one, and then then the two others are entanglement and tunneling. Do you want to take one, and I'll take the other?
Sure. I'll take entanglement, and maybe just to wrap it up on superposition, though. Many folks have maybe heard of the Schrodinger's cat thought experiment, which is a bit of a crude and possibly borders on animal cruelty experiment. But basically, Schrodinger, 100 years ago, created this thought experiment to sort of bring to life what is superposition. And so he said, imagine a cat that is inside of a box, and there is basically a poisonous gas that's hooked up to that box. And you don't know whether the poison is going in or not until you look at the box. And so this cat is sort of existing in a state of both being alive or dead until you observe the cat, in which case the cat clearly collapses into one of those states, alive or dead. And so the cat is in superposition until you observe it. And that's, again, a crude way of explaining what is happening in superposition. But moving to entanglement.
Yeah, just one thing on that analogy. One of the reasons that's been talked about so much for so many different decades is because if you believe in quantum technology, which now we all do, but at the time there was a debate, there was a way of setting up that hypothetical physical experiment to really make it so that the quantum event that would trigger whether the gas was on or off hadn't yet happened.
Right.
And with a probability of 50-50, it would go one way or other. So until that event happened, the cat was literally, if you believe in quantum, had to be sitting in this state of maybe it's dead, maybe it's alive.
50% chance. Right.
How could it be both? And it really has set off kind of, that is weird. The weirdness of quantum.
Very weird.
Yeah.
And continuing on that, the thing that I think really brought it to life was the dual slit experiment, basically, because one of the other elements here of superposition is that particles are both waves and particles, which is very bizarre. So it's called the wave-particle duality. And when you shine a light at a wall, it will exhibit both waves and particle characteristics until you actually put a little observation mechanism in between the light and the wall, in which the act of observing it will have it collapse into either a particle or a wave. I can't remember which one it collapses into, but it's called a wave function. It's a probabilistic function until it's observed. and then it becomes either a wave or a particle. Again, very strange. The act of observation actually influences the outcome.
And it was that experiment that literally led to the proving beyond doubt that this this characteristic called quantum was real world. That was the defining experiment that finally isolated it to a point where you could no longer, as a scientist, deny that this quantum thing is real just because we don't understand it. It doesn't make sense. It doesn't matter. An experiment finally proved it. So a big event. So entanglement.
Yes. Okay. So to preface this, Einstein, the smartest human being who's ever lived, didn't understand this. He called it spooky action at a distance. So he thought this was just spooky, that it defies all explanation.
Not just spooky, but he was implying by calling it that it wasn't real.
Right.
It was come on, this can't be real.
Yeah.
It would be spooky action at a distance. So that was, part of his way of refuting that this thing that looks like, quantum weirdness isn't real. We just haven't figured it out yet. But
so at the most basic level, it's if two particles that are down at the quantum level, at the very small level, they can become, the word we use is entangled, but it's effectively attached to each other in some way, such that if you were to stimulate one of them, the other will respond. And so it all has to do with the way the atoms are spinning. If you observe one and you see it's in a certain state, the other will collapse into the other state automatically. But the very strange thing about this is these atoms and particles will go into this state. One of the things we do as we build our quantum computers is we put them into these states, but they occur naturally out there in the world as well. And it doesn't matter if these atoms are next to each other or if they're light years away. This phenomena of entanglement can occur such that these two atoms will become joined, and if you stimulate one of them, the other will respond. And that's how I explain it.
How long does it take the one to respond?
Instant.
Instant.
Faster than the speed. It's instant.
Yeah, yes. It's instant. Even if they are separated by vast differences, something happens to one which you can affect the one. So you can actually, not only did something happen to it, but I made it happen. I made it come out of the state it was in. Now I can see the state. And you sitting over here can know with certainty and instantaneously exactly what happened over here.
That's right.
Whereas until you did that, it was unknowable.
That's
so
right.
Whatever happened on the other end, no one could have known it until you stimulated. So you think, well, how could that be? How could it be that that these two once connected particles, now separated in space, maybe vast distances, how could you have done something to one of them and instantaneously and with certainty know exactly what happened to the other one? I mean, that's spooky action.
That's spooky action. That's absolutely. And in pop culture, if anyone has read The Three-Body Problem or seen the show, they use a concept similar to entanglement. They call it entanglement, but unfortunately it doesn't quite work that way, where they send some particles to Earth, and at the home planet of the Trisolarians, I think is who they're called, they can then communicate back to Earth, which is kind of how entanglement works. Unfortunately, you can't actually send information faster than the speed of light. And so it doesn't actually work that way, but generally they are playing off the entanglement theme there.
Yeah. I was all worried that the fiber networks we were building, literally in the early days of Zayo, this was post level 3. I'm like, man, is someday this fiber going to be obsolete? And I had to keep thinking about it, reading about it. I didn't have anyone to talk to who knew this kind of stuff, but I had read enough books until it finally fully clicked on me that with certainty, as we said earlier, sitting from one vantage point what happened in another one, but you have no way of telling the other side kind of what happened, other than passing some information through what they would call a traditional media, which means you're going to be constrained by speed of light. It might be a fiber optic network. If it's here on Earth and you shoot, just like we do today, you shoot bits through light to kind of help help make sense of what happened on the other side. You don't have to send all the information, but you have to send some, basically, to then turn it into a communication. Or even more interesting, to actually, as we talked about earlier, to teleport from one side to the other. And what does teleport mean? For those who are, Star Trek fans, they don't, exactly what it means. It means you disappear here and you reappear over there. But again, that event, which is done at very small scales today, so it's absolutely doable. It's being done by humans, setting up engineering devices to do it. How high up in scale can you do it effectively? That is something that will happen over long periods of time. But even as you do it, there's still the speed of light constraint.
Right.
You can't just disappear or reappear there instantaneously. There has to be some kind of communication channel, traditional one, open up at the same time. So, and then the third one is tunneling. And tunneling is talked about less. And I'm not sure I could even fully explain tunneling. We're both lay people, by the way. We're not scientists.
So, yes.
So the scientists in the crowd are probably making fun of us. But the best way to think about tunneling, and it's related to the uncertainty that Matt described, is a particle can, in a quantum state, you kind of know where it's most likely to be, but in reality, it could be anywhere. And how is anywhere defined? Well, if it's close to where it's most likely to be, there's a high likelihood. If it's not the most likely, it's close by. If you're looking at a distance far away, yeah, technically it could be there, but extraordinarily unlikely.
Right.
So it's kind of a bell curve of sorts when you're trying to say, where is that particle most likely to be? That doesn't sound like a big deal until you put it in real world circumstances. And this is actually the story that got me first hooked on quantum. It was when I was graduating from college. I was an engineering degree, and they had some college student come back, and he was a funny guy, and he was trying to explain quantum in a humorous way to the group. And I hadn't even heard of quantum at that point. So I was graduating from engineering, and I don't think quantum ever came up, at least not that I remember. And what he described is what he most got out of the university and his engineering degree is understanding that if he ran full steam ahead against a brick wall and he was willing to do it, enough times, at some point he was just pass through the wall and end up on the other side. He said, but the problem, of course, is I would have to do that for longer than the universe has existed, or get really lucky because it could happen on your first try. It's just highly, highly unlikely. But what that means is you've tunneled through a very thick object. You're all the atoms in your body at the same time went through this tunneling mechanism instead of being where you expect them to be, which is bouncing off the wall with a lot of bruises. You just somehow pass through the wall. So tunneling means that these, at the atomic level, it happens all the time. Small, cold, very cold, they do end up in spots that are different than where you'd most likely expect them to be. And if you could engineer that, you could create devices with it. And that's what's done.
Right.
So tunneling, entanglement, superposition. Those are the three weird effects. So let's make this a business discussion now. So tell us about, you're now out there, you found Dana, you're thinking about getting involved in quantum, you're an investor, you're kind of on the scientific side, like me, a novice. What happened at that point?
So Dana and myself and another investor started having some conversations about if we were to give Dana some seed capital and make a run at commercializing some of the foundational technology that he had been working on at CU, and then also building at what was then called Cold Quanta. What might that look like? And so we started having these conversations, and as we had them more and more, I got increasingly excited about the prospects. And what really sold me at that time was many of the companies that I had looked at that in 2017 were building a quantum computer, and many of the modalities that are out there are uniquely suited to building a quantum computer and can't really do many other things, largely because of the fact that there's a large dilution fridge that's involved. And those fridges are mechanical devices that aren't getting smaller or lighter or cheaper. And so therefore they can't be moved or put onto
So now I'm confused because every time I hear someone talk about quantum, the next word that follows is computer.
Yes.
So I thought the only thing to do with quantum is computing. Is there other things you could do with quantum?
Turns out there are.
Really?
Yes, there are other things you can do with quantum. And that was what really intrigued me about neutral atoms, and in particular what Dana had been building, was that there was an opportunity to build real products based upon these same quantum phenomena that we're talking about, and bring them out to market before humanity reached a quantum computer that could do something that classical computers couldn't do. And at that time, neutral atoms had not really been explored as much as some of these other modalities to build quantum computing, to build quantum computers. But I was highly intrigued about that possibility too, of betting on a modality that was less proven, but seemed to have some real potential for being able to build a quantum computer. So it was a little bit of a less binary type outcome as I thought about it back in 2017, and sort of a multiple shot on goal.
Yeah, let's talk a little bit more about the multiple shots on goal. And let's start with the one people hear most about, which is quantum computing.
Yes.
So when people think about quantum computing,
yes,
and you mentioned before, a quantum computer can do things that you can't do with the classical computer. Mm-hmm. What do you mean by that? What do you mean that a quantum computer at some point will be able to do things that otherwise you can't do?
Mm-hmm. So the way a classical computer works, it's actually quite simple. It's a bunch of circuits that are effectively switches that are a 0 or a 1. There just happens to be billions of these that can be run in different combinations. And when you do a bunch of yes or no, zeros or ones, ands, ors, and put them all into some sequence, you can do all the amazing things that we can do with computers today. Though that way of doing computing is very good for a lot of things, it is very bad at a certain class of problems. And so one thing I always tell people is that quantum computers aren't necessarily, the way you shouldn't think about quantum computers doing the things that classical computers do, but better. You should think about them doing this class of problems that classical computers just have never really been set up to solve. And those largely have to do with situations in which there are many different possible outcomes. And so you can think of drug discovery or chemistry or material science like that, where you're starting to combine a limited number of molecules, but quickly the number of combinations you could have scales infinitely. And so a classical computer, to try to simulate what those might look like, let's say you're going to try to put a bunch of molecules together to make a new drug. The classical computer would need to simulate those serially, and it would just have to brute force it and say, let's try path 1, let's try path 2, let's try path 3, let's try path 4, when there's billions of potential paths. And so the amount of time it would take for a computer to simulate all of those different potential outcomes starts to approach thousands of years, like billions of years in some cases, as long as the universe has existed. And so what quantum...
And these aren't hypothetical things you might want to do with a computer. There's, as you're going to get into these, there's real world questions that you would like to have answers to.
Oh, absolutely. Yes.
That if you relied on today's classical computer or tomorrow's classical computer or a classical computer 1,000 years from now, it just wouldn't have enough time to ever give you an answer to those questions. Yet there's questions that we believe are both commercially valuable and valuable to the to humankind.
Very much
that,
so.
Boy, if you could just plug that in and it give you an answer, wouldn't that be nice? So you touched on this already, but what are some of those questions that you would like to have quick answers to that you can never rely on a classical computer?
Sure.
But maybe a quantum computer could give you a really quick answer.
I often say one, and it's a material science example. It's probably not the best example, but let's say I wanted to build a material that was as strong as steel, as light as plastic, that could withstand radiation in space. If we were to try to build that today, it would require just multiple iterations of combining a bunch of different molecules and just trying things until you could come up with one. That's something a quantum computer could simulate all those different potential combinations instantly and give you the recipe. And so if you think about the implications of just that one example to the real world, how do you build new materials? I mean, I couldn't even tell you the amount of economic value that would come from it. It's not the most intuitive thing because we've never really had the ability to do that before. But that's one example I often give. The other that is maybe a little more tangible.
And second, the materials one, the materials one, think about the materials science that's happened in our lifetimes. What new materials have come to be and how that's changed the world. Styrofoam and plastic and all kinds of stuff. And all that was done over many, many years, decades even, and through trial and error with very limited tools.
Exactly.
By the standards you said, all we had to work with is these things called classical computers. But if you could take all of that, and supercharge it at a level that, it's hard for us to even fully get our minds around. And that's what a quantum computer could do. Like, that was kid stuff, what you guys were doing. That's like, the equivalent of medicine today to medicine 500 years ago.
Right.
We could actually tell you, as you said, give you the recipe. Is this what you're trying to do? Here's exactly what that molecule or collection of molecules needs to look like to accomplish that goal. So a material science revolution of, that we've never seen before will come out of that.
Absolutely. I think the late 19th century with steel, everything that was enabled by their railroads, skyscrapers, we should take it for granted today, but that could be happening on a daily basis with quantum computers. Another example is drug discovery. It's another similar type situation where you're combining different molecules together to see how it reacts. And this is a problem uniquely suited for a quantum computer because the potential of these combinations grows exponentially, and the quantum computer could simulate them all. And so we could be bringing drugs to market that are tailored specifically to an individual human, each person, based upon how it will react to your composition, and it will be revolutionary for medicine.
And maybe even RFK would get behind those drugs.
Maybe, yeah, maybe.
All right, so and like what we've experienced in past technology revolutions, we're sitting here in 2024, sort of scratching the surface, imagining
absolutely
what a quantum computer will really do when it has these powers that the world has never seen before. And the answer is, we don't really know how clever people. And I think some of them will be for good, some of them will be not for good. I listened to a recent podcast on Acquired. I don't know if you've listened to the Acquired.
I love that
channel.
Podcast. It's great. I don't know if I've listened to the one you're about to reference.
Well, RenTech. Did you listen to the RenTech
I didn't.
series?
No.
So, Renaissance Technologies is a hedge fund, the best performing of all time by a lot. Blows
50% compound returns over 30 years or something unbelievable.
So you can imagine, and it consists of a bunch of mathematicians who are whatever they're doing, because the rest of the world, they haven't revealed it, and you can only speculate how they've done it. But they certainly have done it through mastering, kind of applying math to trading that others haven't done. My guess is they already have a large team who are working on what would we do if we had a quantum computer to use as a simulation tool. How could we earn 50% IRR for the next 2 decades?
Exactly.
And you're going to see effects like that
Absolutely.
as well. Okay, so there's quantum computing.
There is,
most talked about.
Yes.
Lots of modalities. The cold atom, which cold quantum Infleqtion is working on, is one of them. They're not quite there yet in terms of quantum computers, but there are regular advances taking place.
Yes.
So let's move past quantum computing and talk about the parts of quantum that aren't talked about as much. And let's talk about what's the next big category.
Sure. So broadly speaking, there's 2 large categories. One is computing and the other is sensing. And there's some things that go under that sensing bucket that aren't you wouldn't intuitively think of them as sensors, like timekeeping devices. But if you think of it in this context, you're sensing time, then it makes a little bit more sense. So if we start with timekeeping. So you can, in the same way that you trap atoms in an ultra high vacuum glass cell to entangle those atoms and start to build a computer, the basic building bones of a computer, you can take that cloud of atoms and actually, by manipulating its internal quantum structure, meaning the valence electrons that encircle the atom, in this case we use rubidium atoms for our clock, you can turn that atom into the ticking of a clock. And that atom but that atom clock ticks 1,000 times more precisely than anything else out there. And by one of these strange things of fate, you mentioned that each atom has a frequency that it responds to, and that you need to find that frequency to work with that atom and start to exhibit its quantum properties. Well, we use rubidium atoms, and the frequency that it responds to is roughly 780 nanometers, which is 1/2 the 1550 nanometers that telecom networks run on. And so there is a very large and robust market for these same double the frequency, double the wavelength lasers that we can just manipulate that laser to bring it down to 780 and start to build these relatively cheaply. And so by
and relatively small too, right?
And relatively small.
So
right.
So this timekeeper that's 1,000 times more accurate, and we'll talk in a second why that matters.
That matters, yeah.
So 1,000 times more accurate than what, the clock I hang on the wall, or 1,000 times more accurate than what?
No, it would be several orders of magnitude more accurate than the clock you hang on the wall. When I'm baselining the 1,000 times more accurate, it's against the gold standard atomic clocks, which are out there today. It's probably getting a little too technical to differentiate how we make our clock versus others, but you can think of it, those are using microwave wavelengths, and so a much longer wavelength and therefore a slower ticking of the clock. We use lasers, very high frequency lasers, which have a much, much faster pulse, and effectively think of it, each time the pulse tick hits, the rubidium atom excites and the electron shoots into its outer valence and then comes back in, out in, out in, out in, and that becomes the ticking of the clock.
Yeah.
So yes.
The gold standard today, basically you say is used to tell the world what time it is.
That's right.
It's like, what time is it? Well, ask the best clock in the known universe. And that's what you're describing as today's state of the art.
Yes.
And why is that important? It's because if we all have different perceptions of what time it is, and all of our devices have different perceptions of what time it is, how do you get things to behave in a way that's synchronized?
That's right. Exactly.
So you need these really accurate clocks that really set the precise definition of the time right now is this,
right?
And everything else has to kind of get their time off of those clocks.
That's right.
But if the time on the most accurate clocks isn't as accurate as it could be, that means there's room to be more optimal, and that's basically what you're describing is a next level up timekeeper that's 1,000 times more accurate, but also can be in smaller form factors, and also can be less expensive.
That's right.
So
yes,
tell us why those two factors begin to matter.
Okay. So historically, to have this level of accuracy that our clock has, it would take a technology that was the size of this room, effectively. So there were clocks that were as accurate as ours historically, but they were a table that would be 10 feet long and 10 feet wide, and lasers and wires all over them. And historically, that's what's been used to keep time, basically. The time stamps that come out of those clocks are aggregated and then sent up into the GPS system, and then every rotation around the Earth, it sends the signal back down, and then all the Earth's timekeeping devices sync up to that in some way, shape, or form. There's sort of a chain there where some devices sync directly to GPS, and then other devices sync to that, and then ultimately you get your time on your iPhone, right? And so what we've been able to do is take that table size technology and shrink it down to about 3 pizza boxes, so a 3U rack mountable form factor. And this actually goes back to a program that DARPA had us run for them 4 years ago, where they basically said, can you take this table size technology and create an actual field deployable rack mounted device? And so we were able to do that for them. And so today we call this device Ticker. It is 3U rack mounted, and we've sold many of them to the DoD. And one of the reasons why the DoD is so interested in this technology is because there's this concept of GPS denial. And so many of the operations that the military does rely upon access to GPS. And if you were to go to continental Europe today, or you were to go to Tel Aviv today, or anywhere around those areas, you're going to find that your GPS is not working like it should. And that's because it's either being disrupted or spoofed. So it's either just being cut off, or it's being told you're somewhere that you're not, or your time signal is being thrown off.
But why did you pick those two regions of the world where that would happen, and why are they behaving in ways where they're spoofed or dysfunctional?
It's happening mostly around hot war zones. Sorry, that's a very, very good point. Yes, it's around hot war zones. The opposing sides, some of the first shots of the wars are taking out each other's GPS. Yeah. And then you have a fog of war around you that you need to be able to operate in. And so our military is very concerned about that. God forbid we do get into a hot war, we will need to be likely operating without access to GPS. And if you think about what is GPS, as I just explained, it is a time distribution system largely. It's a position, navigation, and timing system. But it's sort of a lowercase p, a lowercase n, and a capital T, because the p and the n you need time, right? You basically need time and you need the speed of light, and that's how you know where you are on the planet. And so if you can recreate that level of precision locally on your military assets, or even someday on each soldier, you can have a lot of the benefits that you had to rely on GPS for historically, but you can recreate that locally. And so that's a very high priority for the military these days.
And if your side has it and the other side doesn't have that, they're trying to operate in this fog of war.
That's right.
Where people are operating machinery or moving around themselves, don't quite know exactly where they are. They don't know exactly how to get from here to there. Just like we use our GPS devices on our iPhones to tell us how to get from here to the restaurant. If all of a sudden it doesn't send you to the restaurant and sends you 3 blocks away, you're going to not get to dinner.
That's right.
So if it's not working, not only does it affect the military operation, but it affects everyday life as well.
Oh, absolutely. Yes. So I was just over in the UK 2 weeks ago, and then in the Nordic countries last week, and they're experiencing these GPS denials on a daily basis there, such that the UK has made a mandate where they're going to build what they're calling the National Timing Center. So the country itself commercially is able to withstand GPS denial. And so they're building a network of highly accurate clocks all around the country. So they don't need to hit GPS to have their national time. And the Nordic countries are experiencing these even more. I think there tends to be a thing, and the closer you are to Russia, the more you experience these types of attacks. And
purely coincidental.
Yeah, purely coincidental. They're looking to do
I don't
the
want to
same
get
thing.
on Putin's bad side. So
no, definitely not.
Matt who said that, not Dan. For those who aren't watching it,
so that is one of the use cases of highly accurate time. And if you think about, you brought up a really interesting point. And I love to look to history to find examples as to why this might matter. So in the mid-19th century, in both the UK and here and everywhere, each town had its own time. And it didn't really matter if your time matched up with the town 50 miles away, because all that mattered was the people around you were keeping in sync. But once railroad tracks were laid...
how would you even know? Because
there'd be no way.
The mail comes, or someone comes on a horse. Telegraph isn't, doesn't matter if the telegraph's slightly off time-wise. So being slightly off in time didn't, who would notice?
Just didn't matter.
Didn't matter.
Until railroads came around. And then you needed to keep accurate timetables because you needed to get to point A and point B and trust that you knew when you were getting to point B, it wasn't some different concept of time. And so I was actually reading an article earlier on Monday of this week, and it was like the 150th anniversary of when the U.S. Actually all synchronized on time on 4 time zones. And it was a point in time where one day each town had their own time, and the next day the whole country synced up. And so I use that example because to the people living before that, it didn't really, who cared if we had more precise time? In the same way, living today, and then the huge benefits came from having that precise time. The same way you say, well, why do you need 1,000 times more accurate time than my iPhone?
What would be interesting is when that happened, everyone got on the same time. Was it plus or minus a minute? Was it plus or minus 10 seconds? But it certainly wasn't plus or minus in the nanosecond.
No. Yeah, and then it drifts, right?
Yeah.
And then you have to sync up again. That's the big issue is drift. Because many of us have probably experienced when you get on a long flight and your phone gets off GPS, sometimes you actually see it skip ahead by a minute because even the very sophisticated phone doesn't have that sophisticated of a timing device.
Yep. And then let's talk about other situations where extremely accurate timekeeping becomes important. financial networks,
Mhm.
communication networks, data centers,
That's right.
the GPUs in data centers, energy networks.
Yes.
So all of those, to some degree or another, how they function is constrained by how accurate time can be kept.
Correct.
So differently, if you could keep time more accurately, more things can happen with whatever resources you deploy.
That's right. Yeah. Let's use data centers as an example. There are accurate clocks in data centers today. They're usually those atomic clocks we were talking about. They help provision workloads. They help resynchronize workloads that are being processed parallelly. But time is a bottleneck. And if you can have a finer grained, accurate understanding of time, you can actually pull more efficiency and more usage out of your existing data center infrastructure. And so data centers are a great example where time is one of the inputs as to what your utilization of your GPUs or other data center assets are. Very similar to telecom networks, something you know very well. There are timekeeping devices across the network to time division multiplex signals and to take the utilization of those actual networks, both wireless and wireline. And then finally, the electricity grid is all synced up to very, very highly accurate timekeeping devices. So they're everywhere. I mean, they're truly everywhere. It's billions of dollars of market opportunity out there for just timekeeping devices, which you would not have. High precision timekeeping. We're not talking Rolex watches. We're talking, if you're just thinking of these high precision timing, it's billions of dollars of market opportunity.
Yep. And so we talked about the sensing category.
Yes.
And then we spent a lot of time talking about this big market for very accurate timekeeping. And you mentioned GPS.
Yes.
And GPS does more than just keep time. What else does GPS do? And what's the relevance for quantum sensing?
Sure. So GPS also helps you navigate, right? And so there's many other ways you could recreate all the pieces of GPS using various quantum technologies. And the reason why quantum is uniquely suited to solve these types of problems is because if you can take advantage of some of these weird phenomena we've talked about down at the quantum level, they become highly sensitive. And so one of the reasons you call this bucket quantum sensors is because these atoms in superposition become very sensitive to the world around them. So you can measure things like gravity and movement and speed very, very, very precisely. And so one thing you can build is an inertial sensor. And so today there are inertial sensors out there. They're on airplanes. There are many places. They are somewhat accurate, but we can build inertial sensors that are orders of magnitude more precise and accurate than the sensors that are out there today. And if you can pair up highly accurate time with highly accurate sensing devices and having a highly accurate map, you can effectively recreate GPS without any kind of reference point to a satellite. And so the way I like to think about this is if I were to say, Dan, you need to drive from here into the mountains, and I gave you knew where you started, you had perfect timing, you had perfect sensing around you, and you had a perfect map, you wouldn't need to have GPS, nor would you need to be able to see out your windows, right? You could actually just do that based upon all those external sources. And so you can actually recreate all of GPS using various quantum technologies, and that's called QPS, the quantum positioning system.
Yeah, so a quantum device of the like that Matt described will know with an extreme degree of precision, not just what time it happens to be, but what direction are they going?
Yep.
Are they rotating while they're going that direction? Are they accelerating?
Yep. How high are you? Up or down?
How high are you? So it will know all this stuff about itself without any exposure to the rest of the world.
That's right.
And if you layer on, by the way, we're going to show you a map that has a road, it can figure out how to get from here to there without it needing to communicate with anything else. Doesn't mean it won't communicate with anything else, but the communication isn't a prerequisite. Now, it still will have a drift, but the drift will, by today's standards, will be like, once every month or once every year,
right.
You have to kind of get resynced up to, to be the equivalent of today's standards, as opposed to, once every minute or once every 5 minutes. So you're really allowing the device to kind of exist in an isolated state and maintain a very high degree of accuracy, which not only can be used for a lot of military applications of the type that you were alluding to before, but the commercial uses are probably endless. GPS doesn't do well with height right now. You don't know if you're on the third floor or on the first floor, as an example. Doesn't do well when you're inside a building at times.
No GPS underwater.
Yeah.
No GPS in space.
Not in space, not in water. But if you have these devices who could do within the four walls of the device, can keep very, very, very accurate track of itself, it opens up a broad range of possibilities. And how you combine that with other things is what will produce products and services that are hard for us to fully imagine today.
Yeah. Well, one example, and this isn't a mass market opportunity, but we've had one of our systems up in the International Space Station since 2018, and it's up there running gravity experiments on the Earth's surface to track the impacts of climate change, because it can actually see, here's where polar ice caps are melting, and it can sense that by very, very, very precise measurements of gravity. And so these sensors can be used for gravity. When done from space, you can have a view of the Earth's surface, but also when done from the ground, you can learn things about what's happening underground. And that has a lot of implications for mineral extraction and the like.
And a lot of implications for Graham Hancock. Are you a Graham Hancock guy?
No.
You're not?
I don't know.
Oh my gosh, you are so lucky, because
who's
there
Graham
is
Hancock?
a whole world that will be opened up when you discover Graham Hancock. So Graham Hancock believes there are these ancient civilizations that existed and then largely got wiped out in 9,000 BC.
Okay.
So when there was the last kind of event that caused incredible flooding, perhaps the origin of flood stories like Noah's Ark and many others, and pretty much wiped out most of the remnants of these civilization that pre-existed what we think of as the beginning of civilization. And he's got a lot of reasons to believe that. A lot of proof points. Proof is maybe too strong a word, but a lot of evidence that supports the theory. But most of the evidence is buried in the ground, buried in the oceans, buried in the Sahara that has yet to been explored. So the way you can discover those, and these are being discovered in, for example, all over the world, but including most recently examples in South America and in the Amazon, where you can see through the forest and into the ground and see the remnants of very advanced civilizations. Still debate whether like the traditional archaeologists would still vehemently argue that no, that didn't exist before 9,000 BC.
Right.
But there's certainly solid indications of ones that do. So to be able to explore more of the world, areas that were once not underwater, and what civilization might be buried deep underwater, or in areas that haven't been areas where kind of human life has spent time recently, but maybe has in the distant past. So you should see some of that stuff. It's fascinating.
I'm going to check them out. Absolutely.
Yeah. Netflix has a couple series. The most recent one dropped. The first one, I would start with the first one there, not the second one. And, you can get on any of the big podcasts, and Graham Hancock's a pretty regular guest.
That is, that's right up my alley. I love history, and I hadn't really thought about history 9,000 years ago, but I'm excited to check that out. Yeah.
It's beyond fascinating.
Yeah.
But with the advancement of quantum sensing technology that could see, into the Earth, into the moon, and tell you what's there. The other obvious commercial use of that is rare minerals.
Right.
Where are there deposits of minerals that are extraordinarily valuable and extraordinarily short supply? How would you know they're where to look for them? Quantum sensing is how you would do it, and quantum sensing could bring that up to a whole nother level.
That's right. Orders of magnitude more sensitive.
Yeah. So certainly that's a huge use case. And then you mentioned the two categories of quantum. There's the third category too, which is quantum networking.
That's
and
right.
Quantum
Yes, you're
communication.
absolutely right. Yes.
Both the furthest out, I think, in many ways, but in one aspect, maybe a high priority, because of concerns about cyber security. But the whole quantum network, quantum communication, that's going to require devices that work, at room temperature, hence the cold neutral atom.
Right. Exactly.
And so the neutral atom technology is going to play a big role there because it requires that, not unlike how communications networks work in the conventional world, you have to have kind of equipment spaced apart that takes the quantum signal from one end, does some things with it, and keeps it going to the other end. In this case, it would be using quantum teleportation. That's what will happen at the equivalent of repeater or application sites. But the neutral atom technology is almost certainly going to play a big role in that as well.
Yes, absolutely.
Further out.
And one of the reasons my understanding is it's further out is these are fragile states. It's not easy to keep things in their quantum state. And once you observe it, it goes away. And so with networking, you need to maintain that quantum state and then move it while not taking it out of its quantum state, which is no small feat.
It's basically teleporting.
Yeah, exactly.
Yeah. I mean, that's basically what's happening is the continuous ongoing teleportation of state from here to state from there, and then, recreate it and move it on to the next one. And another reason it's further out, one is just, as you said, the physics reality of it is going to be difficult, but the use case, the narrow use case where it matters in near term, which is, I don't think I want to go down this rat hole, but because it's talked about so much, the encryption and how to protect against what quantum does encryption. But the other use case is you have to have a whole bunch of quantum devices that want to talk to each other and then get tired of using the conventional communication network of having quantum devices kind of interact. So, you know what, we need to keep these quantum devices in the quantum realm, and that will first appear, as it did with internet, it'll first appear in kind of a geographic location, a data center where, quantum devices in a data center need to be connected to each other. This quantum computer needs to talk to that quantum computer on the other side of the data center. Well, we're not going to convert that into classical and send it over traditional network. We're going to figure out how to get them to communicate with each other. But then, then how about this data center talk to that data center?
Right.
How do we connect those two in the quantum realm? So, but that's, 10 years from now, we'll be talking about that from a commercial standpoint.
Right.
But today we're talking about quantum sensing.
That's right.
From commercial. So talk about the commercialization. Like what kind of momentum is developing around checks being written by customers for timekeeping and maybe for other types of quantum sensing?
So like many cutting edge technologies, the DoD and the government in general is a large buyer early on. So our largest customer is still the DoD, and we've talked about the use case why they're buying clocks, and that activity is ramping up. We are seeing activity on the commercial.
And actually, we pause you there because I think this is an important discussion for those who are interested in potentially investing in or directing their careers toward quantum. So, why is a government, why is a DoD investing in quantum? And the answer is they have to. And that's a powerful answer if you're going to be in the business of, I'm going to bet a lot of money on a technology being able to be commercialized. If there is a customer out there who has really no choice but to commercialize it, that means money's going to be spent. So why don't they have a choice? Well, the same reason you didn't have a choice but to develop nuclear weapons.
That's right.
Because if you don't and the other people do,
that's right.
You're going to be speaking their language someday and abiding by their laws someday, because they're going to be able to force you to do so. So it becomes, at the forefront. If you don't participate in the arms race around quantum, and that means not just quantum computing, that means not just quantum encryption, but it also means quantum sensing.
That's right.
If you don't participate in that and you're not a leader of that, you're going to find yourself being far inferior in ability to defend yourself than a country that does do that. And if you're your enemy, you got a big problem on your hands.
What makes it very real for me is I've spoken with many generals in the last 2 months, and every one of them brings up this idea of having to operate in a GPS-denied environment and the fear of what that would be like. And just it's very motivating to want to get this technology into the hands of our soldiers for two reasons. One, if we did get into that situation, we would have a huge advantage. But the knowledge that we have this is a deterrent to the other side from starting a war.
Yeah. And that's just talking about GPS denied environment, but then you take the other capabilities that you touched on, and you're able to do things that otherwise can't be done. You could see around buildings. You can't see around buildings with today's technology, but with quantum technology, if there's someone hiding on the other side of that brick wall, the way quantum works is it would be able to sense that there's something over there, and makes sense to say there's a person behind that brick wall that has a gun and might be wanting to point at your direction, or behind a mountain range. So we talked about submarines. You can't detect submarines today.
No GPS. Yeah.
But if you had the right quantum technology,
you certainly
know where the other side's submarines are, and they wouldn't know where yours are. So the deterrent aspect of it, if you have these kind of capabilities and the other side doesn't, you could use that as a force of good, deterring battles. If the other side has it and they don't have the same belief system maybe you have, they could use it as a way to gain control over your resources, your people, your country.
For those of you who have read Chip Wars, you probably remember that the early markets for the transistor and the microchip were missiles and rockets and precision guidance. And, the ability, I remember this one chapter where they were trying to bomb a bridge in Vietnam, and there were just pockmarks all around it. They couldn't hit it with that technology, but once Texas Instrument was able to put one of their specific guidance microchips in there, they were able to hit the bridge. And I don't like thinking about the violence that comes along with this, but it is a fact of life, and this is the next evolution of precision. And
do you know what sparked the internet to be created?
Worry about a nuclear attack, right? Redundancy from a nuclear attack.
Exactly. It was Russia putting up the first satellite. Sputnik is, I think, how you pronounce it.
Yeah.
And it'd be like, they are getting ahead of us.
Yeah.
And what happens if we're in a nuclear aftermath situation? How are we going to communicate? We need a system that isn't relying on kind of, the traditional communication network of information being passed from one point directly to another point in sequence. We need information to move around. So the concept of, wouldn't it be nice if we had this packet network, but they had to invent it, and that became the internet. So it is really important to, I think, for people to realize, even people who are, which I think at some level or another we all are, disgusted that we have to fund stuff from the perspective of warfare. Whether you think about it as defense or offense, it still is war.
That's right.
But if you don't do it,
that's right.
You got a much bigger problem on your hands.
That's right. Exactly.
But as an investor, it's a way of like being able to lean much more heavily into the investment in these kind of technologies, because you know that there's going to be a funding source to really get it to the point where it's developed enough that it then has commercial use cases.
Right. So the military is a big purchaser of many of our quantum sensing products. And then the US government is a big funder, mostly through the national labs, but DARPA just announced a big program also of purchasing quantum computers too. Now, whereas you can buy a quantum sensor and today have a real world, several thousand percentage increase in your ability to perform. So huge advantage to buying those sensors. There isn't that advantage yet for computers, but because it's of such a mission critical nature to get the quantum computing capability here for our country, the government is willing to fund the purchases of computers that don't yet do anything interesting, because they know that that's going to keep, pushing us towards that day when we do have that computer that does something interesting. And so I often think about a sale we make being a sale that is not commercially valuable versus a sale that is. And I put a big difference between those two. And so our sensing products actually do deliver real improvements in performance to the military. Whereas we've sold computer systems to the government that are systems that don't do anything useful yet. So military, a big buyer of the sensing products. Increasingly, we're seeing, though, interest from data centers as well as telecom networks, and for the very reasons we just already discussed. Another really interesting burgeoning market, though, is this one I was describing before, where you're seeing countries putting out these nation-state level timing networks to have super accurate time in the absence of GPS. And so metrology labs are another early buyer of this technology. Now, today, our units are about $225,000. So they're not cheap. And we earn a pretty good gross margin on that $225,000. The really interesting thing, though, is that if you were to open up the pizza box that I was describing to you, it's a lot of lasers and a lot of wires. And those can all be integrated down into photonic integrated circuits. And that's not physics, that's just engineering. And it's a well-trodden path to do these types of integrations. And so we have people internally whose job it is to take these laser systems and start to integrate them down. And ultimately, after a lot of work and integrations, these can be chip scale level and can be significantly less expensive than they once were. And that really broadens the market opportunity once you can have that level of precision at a much, much lower price point and smaller form factor.
Great. So a famous, I think it was Mary Meeker put this out, a famous paper came out years ago that I think was titled Software Ate the World or is Eating the World or something like that.
Mark Andreessen, I think Software Eats the World, yes.
Yeah.
Your fellow University of Chicago, University of Illinois alumni.
Yeah, I mean, he's overshadowed me a tad. But I'm going to get him back with these quantum investments.
Right, exactly. Yes.
So one of the things I'm most excited about as an investor in Infleqtion, and I know you're very excited about as well, is that there is a software layer that is maybe a fourth category, but cuts across the other categories.
That's right. Yeah,
a software layer that is that needs to become multifaceted over time. If you think about like software that is needed for getting traditional computers to work, and then an application layer on top of that, which is software.
That's right.
So what are you guys doing with software and why is that a big deal?
So we believe deeply that where we are in the technology curve for quantum, you need to have a full stack solution. You need to have the software and the hardware integrated. Over time, that may separate like it has in classical computing where folks will specialize on software and folks will specialize on hardware. That makes a lot of sense. But today it has to all work well together. I think of it as IBM mainframes in the 50s. You bought one of those and you bought a whole system that came ready to go. So our software really does two things. And the guiding principle that we've used is building CUDA for quantum. And CUDA is the software layer that NVIDIA has pioneered, which has become an absolutely huge moat for that company. And our software does two things, much like CUDA. It's a middleware layer. And so think of it as a compilation layer, so a compiler. So where you can, even if you don't know how to code in quantum language, you can code in a language that feels pretty similar to what you know. And this will turn that into quantum language and then do all the weird things that you need to do down at that atomic level to stimulate the atoms with the lasers and actually run the calculations that you want to run. So one of the,
and then bring back the information.
Then bring back the information. Exactly. Yes. So that's one layer. So that's think of that as like the middleware compilation layer. And that interestingly works for our computer, but also works on different modalities. So we've designed it so it's modality neutral, but modality aware. And so it will adapt to a certain extent to work on the various modalities. So we have it running on superconductors. We have it running on trapped ions. We have it running on electrons over helium. Many different modalities are running this quantum compilation software. And one of the things it does is it just allows you to enhance your performance of your underlying hardware. And so you usually see about a 10x increase in performance when you run this software on top of your hardware infrastructure. So that's one layer of what we do. The second layer is an application layer. And so trying to actually build software to do interesting things with quantum hardware. And so there's been some interesting emergent unexpected, I guess almost what would be the right way to say this, but I guess I'd just use unexpected and surprising things that have come about as we've built this application layer software for quantum. When you're building quantum software, you have to just make it different because it has to take into account the laws of quantum physics. And so there are just things like you can't copy and paste data in the quantum realm. You can do that in the classical realm. So you have to write around that as you're writing software. And there's a bunch of other things. And I'm going to do a reasonably sloppy job of explaining this, but just say you got to write software differently for quantum. It turned out that when we apply that software onto GPUs, we see some pretty impressive performance enhancements of those GPUs, mainly because quantum software thinks about memory differently. And so it does matrix multiplication differently. It doesn't do columnar multiplication. It does it more of a scatter plot. And it has to do with some of these underlying laws of quantum physics that you have to take into account. And one of the things it's proven to do, and the application that we're really working to productize quickly today, is it helps you expand your context window in GPUs. And the context window has been historically one of the biggest bottlenecks in scaling up generative AI. And so the rule of thumb is, as you double your context window, you need to 4x the amount of GPU capacity that you utilize. And context window, think of it as like a proxy for the amount of data that you're throwing into the GPU. And so whereas you can throw...
And the amount of power that you have to throw into to power those GPUs.
To get the answer, exactly.
Which is a huge part of the cost equation.
The perfect example for an immense amount of context is, and I think, I think it was on the All In podcast, actually, I was listening to, where they had Elon Musk on, and he was describing and using these exact words: the context is too big. All of the video and sensor data that he's amassing from all of the Teslas out there in the world, he can't really do much with it because the context is just too big. It's too much data. And so streaming sensor data is a perfect example of a massive context window problem. When you apply our software onto GPUs, and this isn't a panacea, it's not going to solve all these problems, but it helps make these GPUs process this in a much more efficient manner. And so it takes that scaling ratio from doubling to 4xing. So if to double the context window, you have to 4x the amount of GPU capacity and power. To when you double the context window, you only have to 1.4x the GPU capacity and power. So a very, very large increase in utilization. So it's something we're exploring in a big way right now.
Yeah, because if that proves to play out, I know it's early, but if that proves to play out, and again, thinking about, I mean, they're talking about like the amount of power capacity increase that is needed. I'll talk about the U.S. I'll use U.S. as a reference point to support AI is, 20%, 25% increase in the entire power supply. Well, what this would say is, yeah, you're still going to need 20, 25%, but as you're getting that 25%, you're going to have
way more,
more, which means you could take longer to get there.
Right.
It will still be a constraining factor, but the constraint line gets flattened a little bit, more than just a little bit. And that's, trillions of dollars of investment we're talking about.
So the way we're thinking about this today is we're not going to go just try to apply this to the biggest large language models. We're focusing our efforts on the edge. And so the small GPUs that exist out on vehicles and phones, et cetera, where there isn't a lot of memory locally, but they have a lot of potential data to process. And so we actually just signed a contract with the Army to explore this and in fact, use it to try to recreate some of the aspects of GPS via software with the sensor data that's coming in. So potentially a game-changing technology.
Yes.
And from a power, we should talk about power consumption a little bit, because that's another big area where quantum can help a lot in terms of what you were saying. They're talking about firing 3 Mile Island back up to power data centers. So we're talking creating net new nuclear power plants to fuel GPU clusters. I'm not kidding. We actually use hair dryers as our metric for how much power is being consumed for our quantum computer. So our quantum computer runs on about 5 hair dryers. And the interesting thing is, and that quantum computer doesn't yet do anything that a GPU cluster could do. But as we scale it, because its power scales exponentially, its power meaning its computing capacity, its power consumption doesn't scale exponentially. So we're talking, what would be the most powerful supercomputer in the world running on a dozen hair dryers or something like that. So it's a very, very power efficient way to do computing.
Yeah, when one of the previous guests on here, podcast that we just dropped a couple weeks ago, was with Corbin from Maybell,
right?
Who does these freezers, ice boxes for the modality of quantum computer that needs those. And
Corbin's the smartest refrigerator salesman I know.
He is. Yeah. He is a good salesman. And I mean that in the best possible ways, Corbin. But one thing we talked about is exactly that. We always say that when you talk about quantum computers, quantum computers can solve problems that conventional computers can't solve, but conventional computers are good at solving what they do. Well, they're good at solving them and consuming a lot of power is what we're learning in this new AI world.
Absolutely.
What if you could solve conventional problems with a quantum computer, and the value add of using a quantum computer instead of a conventional is it consumed a lot less power?
That's right.
That would be a really big deal.
Very much so.
Yeah. So the use case, like what's the silver bullet use case for quantum computing? Do things a classical computer does, but do it with a lot less power.
Could be. Yeah,
that
sure.
Could be one gigantic one
Very
in the
much
early stages of it. So let's talk about the other thing about quantum software that I think is being underestimated by most, but probably being already exploited by the clever few.
Mm-hmm.
And I'm going to use the Rentec that we talked about a little bit earlier as an example. So when quantum computers achieve this quantum supremacy, meaning they could solve real world problems that are valuable that cannot be solved by classical computers. So that's one way of saying quantum supremacy. You've crossed that line of you're doing things that you can't do, and the things you're doing, aren't just hypothetical, fabricated examples that have no commercial relevance. They're things that are commercially relevant.
Yep.
Okay. When that happens, there's the capacity of the quantum computers can do that is going to be very constrained.
Yes.
Right. It's not going to be, you've solved that. Now there's gazillions of quantum computers all over.
No.
There's, handfuls, and then there's, handfuls times 4, handful times 8, but small amount of capacity. Well, that capacity, when it's first available, is going to be like anything, a very valuable commodity that's available in very short supply.
Yeah.
And why is it valuable at that stage? Because maybe you can discover new materials.
Right.
Maybe you can discover new drugs. Well, who's going to be in a position to take advantage of it? Well, it's going to be companies that's already spent lots and lots of time already developing the capabilities, the skill sets, the tools on solving drug discovery with a quantum computer before a quantum computer was ready for it.
That's right.
So they've used these simulations, they've used their know-how, and they're saying, we got to get ready and we got to be ready to pounce on that.
That's right.
So if it's a Rentec example, who's used to making 50 hours, they could already have a large team of people working, behind closed doors saying, we are going to be the first to take advantage of this to create, trades that can only make money because we can discover patterns that are otherwise invisible.
Right.
And we're going to know how to do that. So we're going to be the first ones to rent capacity on the first available computers, and we're going to make a fortune doing it. So, whether you're a pharmaceutical company, whether you're a material science company, whether you're a trader, investing early in how to build and leverage software and be able to work with a company that has the software layers that you need to plug into, so you know how to jump into that.
Right.
Now is the time to be doing that.
Exactly.
And I'm sure there's lots of clever few who have already figured that out.
Yep.
But they're doing it very quietly, is my guess.
Going back to, we were talking about why is the government funding quantum computing? Part of it is to get, even if they can't yet do something that a classical computer can't do, get people working with them, learn how to use them, understand the basics. So when they do come out, like you said, we'll have people who know how to utilize these things, and that'll be massive commercial advantage to the companies who can take advantage of it.
Yeah. So one of our goals is to penetrate Rentec, whoever's working on this behind those closed doors, and get them to know who you guys are.
We'll sell you a
do
computer for $1 billion and you can make $10 billion. Seems like a pretty good change.
Sign an NDA with them, and they'll be all
right.
over what you guys are doing. You touched on this earlier when you talk about the UK example, where they want to build a timekeeping capability for their country. Now, as you know, I come from the network world.
That's right. Yeah.
And I like to use my world as an analogy on some of this stuff. And one of them is in the early days of the internet.
Mm-hmm.
So the early days of the internet, it wasn't called internet, it was called an ARPANET. And even before then, it was really, they didn't use the word local area network, but when it first started, there were a handful of servers interconnected together. But as as the internet began to grow up, you then had these, not everyone was going to have their own private network of routers connect together with, private connections that belonged only to them, and it had to turn into a shared network, a network that, lots of entities could tap into, both to use for their own purposes, but also to create, information that flowed between, entities that weren't in the same company. It became the internet. Well, the same thing is bound to happen, and probably is already beginning to happen with some of the quantum, and maybe timekeeping is a good way to think about it. If you were the UK and you wanted to, which they do, and they're already investing in, they want to create a timekeeping for the nation, that probably implies someone's playing the role of service provider. That they might be buying capability from Infleqtion and others and deploying it, but then they're operating, in this case, maybe a timekeeping network that others then tap into in order to be part of this, accurate time. What kind of activity of that nature are you beginning to see, if any?
Well, as I understand it, if we just use the UK example, it's quite interesting. So I was actually at the NPL, which is effectively the UK's equivalent of NIST. And they have a very interesting structure where they're both a publicly funded entity, but they also have a mandate to go generate commercial revenue. And so they actually do sell highly precise time to the City of London, for instance. So they will, I believe, be the operator of this system and generate revenue from that. Now, over time, will they transfer that operation to a private entity? Possibly, but as I understand it, it will actually be the National Metrology Center that will run it, but charge for that and earn a revenue stream based upon it. But there will absolutely be huge opportunities to be network operator of some sort in the quantum realm over time.
Yeah, and I would think clusters of data centers might prove to be an early use case for that. Perhaps financial trading networks, where you have to keep track of exactly what is the time in Chicago relative to New York, relative to London, so that the trades get stamped at a level of accuracy well beyond today. And today's capability, instead of each firm having to build out its own timekeeping network, maybe there's an opportunity to build out a network that does timekeeping. So,
absolutely. I would think timing as a service would be a very natural way for this to evolve over time.
Yeah. So let's see, what have we not talked about that you'd like to? So tell us a little more about this guy, Dana Anderson.
Sure.
Dr. Anderson.
Dr. Dana Anderson. Yes. Well, he's a legend. Yeah, I'll tell you a couple things about Dana's history, actually, which is quite interesting that you might not know. Dana's a little bit like physics nobility in some ways, in that his father worked for Enrico Fermi at the University of Chicago.
Oh, yes.
I
would not have remembered that, but now that you said it.
It's pretty incredible. Yeah. So Dana grew up remembering Enrico Fermi when he was a child.
Wow.
They're pretty neat.
As I hear that name, I think of someone from the 1800s.
I know, exactly. Yeah, we love you, Dana. Yeah. Also, I learned that, so there's a very strange way that you refer to your PhD advisor. And you refer to them as either your father or your mother. And I didn't realize that, but it's your PhD father or your PhD mother. And the folks you go through your PhD program with are your PhD siblings. Or at least that's how Dana refers to them. And he's told me that's common. I
won't make any remarks about it in this pronoun-sensitive world.
Very strange.
What variations are there?
Yeah, exactly. Well, Dana's PhD, either grandfather or great-grandfather, was J. Robert Oppenheimer. Amazingly. Wow. So his PhD advisor studied under a PhD advisor who studied under Oppenheimer.
So speaking of scientific royalty, tell us about your other, if I remember right, example of royalty. So Mark also has kind of lineage that was deep into the scientific world.
Definitely. Mark is, I don't actually know if I know Mark, his personal history, but I actually don't know his.
There is some lineage there.
Is there? Yeah. I got to ask Mark. So usually these come out after a couple glasses of wine with Dana. I need to get into that situation with Mark and learn about that. But it would not surprise me.
So tell us about Mark. Who is Mark?
Mark Safman. Yes.
What's he
Mark
do
Safman.
for you?
Mark Safman is our chief computing scientist. And so Mark was one of the first people to explore neutral atoms for computing. And so Mark did his, I believe, PhD and postdoc at Caltech and has been a professor at University of Wisconsin-Madison for about 20 years probably. Mark is an absolute genius, and Mark is pushing the limits on what can be done for quantum computing with neutral atoms. And so Mark is a pioneer of what we're calling dual species. So it's a way of doing our quantum computing, but using two different species of atoms, both rubidium and cesium, instead of just choosing one species. And what's interesting about that is that a lot of what you're trying to do when you're building a quantum computer is, for lack of a better term, trick the laws of quantum physics. You're trying to make measurements and observations without collapsing the quantum state. And that gets really tricky. and
especially if you're Schrodinger's cat, because you can be in that state for a long time.
Exactly. And so with this dual species, we're able to actually observe one of the species without interfering with the other species' quantum state. And so that's what Mark has been really pushing recently. But when I think of Mark, I think of just always at the cutting edge of what's going on in neutral atom quantum computing, and that's his life's work. And so he's both a professor at the university and then also works with us on our quantum computer.
Yeah, it's again, coming from lay people here, so I'm looking at camera, forgive me if you're a scientist and you just shake your head, but I think it's worth talking a little bit about what you had just said, where you're trying to trick physics. So the way qubits kind of get to the good answers to the question you pose of it is qubits have to get in this entangled state. And they need to, stay there such that you can make sense of what the entangled state is. Okay, so as we said earlier, when we were talking about what is entanglement, we said if you basically in any way interfere with an entangled particle, usually, think of it, you observed it, but if there's any interference, if it pops out of its entangled state, that's what causes you to know what happened at the other one.
Right.
Okay, but if you have to cause it to go out of its entangled state, anytime you're trying to get information out of it, well, the computer's not going to be very reliable. It's going to constantly be falling out of its entangled state before you can even tell what happened. And so the trick is, I need to get this large collection of some type of particle to enter this, what we would think of as an unstable entangled state. Mm-hmm. And I need to use that entangled state to address whatever I'm trying to address without breaking the entangled state at the same time.
Right.
So, the bigger you want to make that entangled state, the exponentially more complex it becomes. So that's what you're trying to, when you say trying to trick physics, it's how do you accomplish both at the same time?
Exactly. Yeah.
Okay, so that's a little bit about Mark. And then I want to talk a little bit more about you and specifically your transition from investor.
Mm-hmm.
Which we talked about early on. You got involved with this as an investor.
That's right.
And we're, I don't want to say just investor, but relative to what we're going to talk about, you were an investor, board member, active board member of Infleqtion for the first number of years.
Mm-hmm.
But now you're sitting here as CEO.
That's right. Yes.
So two questions. How does it feel to be a CEO?
Yes.
This is your first gig as a CEO. So how does it feel to be moving from being an investor board member of, in general, but also of Infleqtion, to being now the CEO who's going to deliver?
I love it. I feel energized, excited, challenged every day. And I feel just very honored to have this opportunity. I love this company. As you said, I was involved as a board member for many years, and I so want to make this company successful. And so it is, as you know, being a CEO is a hard job. And I worked with many CEOs along the way as a board member and always had huge amounts of respect for them because I knew intuitively that it was a very hard job. I can confirm.
Well, you're one of the very few investors who knew that being a CEO is a hard job.
Yeah,
most of them think that's easy. And being an investor is hard.
Yeah, I would. They both have their challenges, but I can confirm firsthand that being a CEO is a hard job. But it's just an incredibly meaningful one, and I feel very blessed and lucky to have the role I have today. And so I love it. And I'm still on the very steep part of the learning curve, but that's sort of where I like to be.
How's your sleep patterns?
There's not a lot of sleep these days. And if I do, I'll wake up in the night thinking about an org chart or something like that.
Yeah. And then lastly, I know we're getting toward the end of the time here. You have lived in the Valley, right? You're a Silicon Valley guy.
That's right.
How long have you lived there?
I moved there from New York in 2014. My wife is a native. She grew up in the city of San Francisco, but we've lived in Silicon Valley since 2014, but we'll be soon a Boulder resident in June of next year.
Good. So as you're starting to get to your feel for the Boulder, the Colorado area, with the reference point being Silicon Valley, what similarities do you see? What differences? What excites you? What makes you scratch your head? Like, what's the big deal about Colorado? What's your sense of what's going on here?
When I first got to Silicon Valley, I really got curious about how did it become what it was, what it became, because it wasn't always that. And so I actually wrote this post on LinkedIn. It's the only time I've ever written a post about it, which was the history of Silicon Valley. And there are a number of some components that you need to have to create what Silicon Valley is today. And when you don't think about this, when you drive down the 101, you pass Moffett Field, and you pass that gigantic hangar, and you wonder, like, why would you need a hangar that big? Well, it turns out it was a blimp hangar, and back in the 30s, that's what the military thought was going to be the next big thing. And so they put this state-of-the-art field there, and then brought all of the technology companies of the day around to service that blimp industry. And so you had this pull from a bunch of technology companies into one area. Then on top of that, you layer great academic institutions, right? You have Stanford, and you have Berkeley, and then you have random things like William Shockley. He happened to grow up there. So when he started Shockley Semiconductor, he came back to the Bay Area to start his company, and then it just sort of starts to snowball, right? And what I sense here in Boulder is the beginnings of that type of ecosystem developing, and many of those same foundational components being present. And then the last thing is it's a physically very nice place to live, right? Both the Bay Area as well as Boulder. And so you have a world-class academic institution, especially in physics here at CU Boulder. You have a lot of the military and government institutions around here. You have a burgeoning technology industry, which has spun out of that university. And then you have the pull of this just being a wonderful place to live. And then you have people like yourself who've been longtime residents here, who are just big boosters for quantum, who are sort of willing this and pushing this and stimulating this ecosystem to develop. And so it's very exciting. It feels like you're at the beginning of what could be a Silicon Valley type scale. And then you layer on the fact that we just won this EDA Tech Hub designation. And so I think we're just going to feel the gravity keep pulling here to Boulder for quantum. And so it feels very exciting to be here, and it's just a wonderful place to live.
Yeah. Well, as an investor in Infleqtion, as a Boulderite who cares deeply about our entrepreneurial ecosystem, as a Coloradoan who cares about the Colorado ecosystem in a broader way, I'm glad you're out here, and I'm glad you're at the helm of Infleqtion, and I'm thrilled to have you as a guest on this podcast.
Well, Dan, thanks for having me. It was a pleasure. And thank you for all that you have done for the quantum ecosystem. I know some people know how much you've done, but you've done a lot for it, and Boulder in general. So thank you.
Great. Thanks.
Yeah. All right.
Thank you for listening to this episode of The Bear Roars featuring Matthew Kinsella. This podcast was produced by Loud Bear Productions and edited by Kendall Weinberg with support from Courtney Caruso, Emily Reed, and Gibson Siegert.